So welcome everybody to this new session of the student seminar. This time we're going to have here Avelino Vicente. He did the PhD in Valencia, like 3 years ago, more or less. 4 years ago. Then he had done a postdoc in Saclay.
In Orsay.
Sorry. But then after he did and now in fact he's still doing the postdoc in the University of Liège. So he's going to talk about lepton failure violation, as you can read from the title, and of course you have to do all the questions that you want to him, and he's going to be very pedagogical.
I'll try. Okay, well, thank you everybody for coming. It's a great pleasure to be here. Actually, I gave already a pedestrian seminar 5 years ago. That was a long time ago when I was doing my PhD, and I must say that now there are even more people, there are more pedestrian seminars, so I have to congratulate the organizers. This is a great job you are doing. And well, before I begin, I would like to make a comment. So it's actually, in physics, usually when there are two things which are the same, we believe there is some reason behind, some symmetry. And in fact, I found something very curious, very fascinating, which is that this week there are 2 seminars given by a person with a name Avelino. So tomorrow there is another seminar, and today my seminar. I think this is something very strange, because there are very few people with my name. So there must be something behind this, some explanation. Anyway, now let's begin. So this is the outline of the talk. First, I will give a very general introduction to the lepton sector, some questions, some open problems. Then I will move to the main part of the talk, which is lepton failure violation, which is going to be also quite general. And then in the end, if I have some time, I would like to discuss some hot topics, some topics which are now discussed in the community, which are lepton failure violation in low-scale seesaw models and Higgs lepton failure violating decays. And then I will conclude with some final remarks to motivate further research. So let me begin with the introduction. Well, you know that before the LHC started, we had many hopes. We thought that everything was fantastic, that we had many chances for discoveries, and we expected something like this. So basically, we expected to discover supersymmetry, extra dimensions, black holes, compositeness, everything. Basically, that was our expectation before the LHC. Then we opened the box, and we found basically this. So basically nothing apart from a little thing, which is, of course, very important, this palm tree, but nothing else. So, and this actually was somehow expected. We all expected to find the Higgs. So this brings us to the question, is there any good reason to go beyond the standard model? Or is it possible to live within the standard model and have everything explained? So of course, we do have a good reason, and this is basically neutrinos and the lepton sector. And as I will explain later, there are still many things to be understood in the lepton sector. And this is, in my opinion, the best motivation to go beyond what we know about the standard model. Now, let's talk about the standard model. Well, one of the things that is really interesting about this is that there are 2 types of fermions, as you know. There are quarks and there are leptons. And about quarks, we basically know everything, but we don't know how to calculate, because it's very complicated. It's non-perturbative physics. Or we know how to calculate, but it's really complicated. And with leptons, we know how to calculate. It's trivial. But there are many things we don't know. And this is a very interesting difference between the 2 sectors. And because of that, doing physics in the lepton sector is something very nice, because you can speculate, because there are many things you don't know. So you can invent new models, you can create new paradigms, new ideas. And it's kind of funny. I mean, you can play with it. And this started some time ago. This is a very nice letter. Maybe you know the story. So this is the invention of neutrinos. This guy here is Pauli, Wolfgang Pauli. And in the 30s, there were several experiments studying beta decay, a nuclear process. And they were measuring the energy of the electrons that were coming out of beta decay from the nuclei. And they found that these electrons had a continuous spectrum with different energies, going from some minimal energy to final energies. And this was a continuous spectrum. And that was very surprising, because they were seeing these electrons, and they knew that there were new nuclei after the decay, and that's a 2-body decay. And when you have a 2-body decay, the energy of the particles in the final state is determined. It's unique. You can calculate it. So you don't expect a continuous spectrum, but a given line. You expect that all the electrons would have exactly the same energy. But they were not observing that. They were very surprised by this, and actually they were making all kind of hypotheses. So some people started to claim that maybe energy is not conserved. Maybe at the microscopic level, energy is not conserved, and then we have to change our paradigm of physics, and people got crazy with that. No? And then there was a conference in 1930 in Tübingen, in Germany, and Pauli couldn't go. I think there was some reason, some personal reason he couldn't attend, but he had an idea. And he said, okay, let me send this idea with a letter to my colleagues. So he started the letter in German, of course, but it says something like, "Dear radioactive ladies and gentlemen," and then he explained his idea. And the idea was, okay, maybe there is another particle that we cannot see that is escaping the process, and we cannot detect it, and this particle is taking away some of the energy that we are missing. That would explain why the electron sometimes has more energy and sometimes less, because they have to distribute the energy between 3 particles instead of 2. And he felt a little bit sorry about that, because he said, okay, I'm proposing a solution that cannot be discovered, because this particle would interact with matter so weakly that we will never be able to discover this particle. He was kind of feeling guilty about that. Now we don't do that. No? We just propose new particles. We don't care about whether they will be discovered or not. That was in 1930, and just 4 years after that, Fermi, who was a wonderful physicist, proposed the first theory with the neutrinos. And he also invented the name neutrino, because actually Pauli called it neutron. Then when the neutron was discovered, Fermi decided that this was smaller in a way, so he decided to call it neutrino instead of neutron. And so he proposed this Lagrangian for the interactions of neutrinos with the protons and the neutrons in the nuclei. And well, this theory was actually very successful in reproducing the results. And well, I think this is very interesting, that something that was created as a speculative idea had very good results immediately. And a few years later, actually a bit more than 4 years, actually 26 years later, neutrinos were actually discovered, and this was done by these 2 guys. These are Cowan and Rines. They were in the US, and they did an experiment, a very clever experiment. They discovered neutrinos. Actually, they discovered antineutrinos by using this process. So they have here some water, and then they realized that neutrinos would be produced in massive amounts in nuclear reactors. So they put the detector next to nuclear reactors. Then they had a huge flux of neutrinos coming to water, producing this reaction. And the discovery was claimed because they were able to observe both the positrons that were annihilated with electrons in the medium and the neutron that was captured by cadmium simultaneously. And because of that, they were able to discover neutrinos. And that was something fantastic, no? And also was a proof that Pauli was wrong, because neutrinos could be discovered. You just need to put a lot of material and to have a huge flux of neutrinos. But in principle, you can do it. Now, the problem with all these things is that neutrinos were discovered, some of their properties were measured, but in principle, everything was consistent with the neutrinos being massless, with a mass which was exactly 0. And that was something that, okay, nobody could prove that that was the case, that they were really massless. They could have a very tiny mass, but for simplicity, the fathers of the Standard Model, which are here, decided that, okay, let's create the Standard Model with massless neutrinos. That was a practical decision. There was no fundamental reason to do it. Just, okay, we have no reason to believe they have mass, so let's suppose they are massless. And then they decided not to introduce right-handed neutrinos in the Lagrangian, and because of that, you cannot construct the usual Dirac masses that you have for the rest of fermions. Also, this is a bit more complicated to explain, but the fact that neutrinos are massless in the Standard Model is not only because there are no right-handed neutrinos, but also because the lepton sector is minimal. There are other ways to give mass to the neutrinos, even without right-handed neutrinos. But the point is that they didn't have any reason to add any mass for the neutrinos, and that's why they decided to suppose that they were massless. However, there were some experiments also looking for neutrinos, which were finding some anomalies. For example, when people started to build very nice theoretical models about the sun, they were able to compute the number of neutrinos you would expect to come to Earth. So they get a number. Okay, I expect to get this number of neutrinos. Then I put my detector, and I calculate how many of those neutrinos will be detected by my detector. And they were finding in a consistent way that they were always getting less neutrinos than expected, about 1/3. So in the beginning, they said, okay, maybe my theoretical model for the sun is not that good. Maybe there are more processes in the sun. The sun is a very complicated thing. There are many things happening at the same time. So maybe we are not computing this properly. But let's say that even after improvements of the model, the number didn't get better. It was always less than expected. At the same time, some other people said, okay, let's suppose some cosmic rays come to the Earth and they hit the atmosphere. In the atmosphere, you have some particles, atoms, many types of atoms. But in these collisions, you will produce some pions. And when this pion decay, you expect to produce 2 muons for each electron. It's something very simple. So pions typically decay to muons, and muons decay to electrons. And in each of these decay, you produce a neutrino. So in the end of the chain, you expect 2 muon neutrinos and 1 electron neutrino. And they said, okay, let's see if this is what happens. So they built again detectors, they put them in the Earth. They were looking at the sky, trying to find these neutrinos. And they found that the ratio between the number of neutrinos with muon flavor and the number of neutrinos with electron flavor was not the same. Again, an anomaly. What's going on? So these were some anomalies, and for many years, this was an open question. What is happening? Why cannot we find all the neutrinos we expect? And then, thanks to some further experimental developments, this question was solved recently, actually, in the late 90s, by something called neutrino oscillations. And this is something very simple. It's just quantum mechanics. The idea is that you have different types of neutrinos, and since they are not neutrinos with definite flavor, don't have a definite mass, when they propagate, they oscillate. So you start with some composition of neutrinos with some definite flavor, and in the evolution, this composition changes. So you have an experiment that is looking for, let's say, electron neutrinos. You will miss some neutrinos because they have oscillated to other flavors. So you have to measure the 3 of them to find all of them, because some of them will be in a different flavor. That's simple. But this has a very important implication. For this process to take place, you need neutrinos to be massive. And this is the key point. So when neutrino oscillation was finally established, we learned that neutrinos cannot be massless. They have to have a mass. And this is the main outcome of all this story. But there is something else. There are other experiments that have been trying to measure neutrino mass. Now that we know that neutrinos are not massless, they have a mass, the next question is, what is the size of this mass? And for this, there are many experiments, and each one of them has tried to do it better than the one before, and they have all failed to measure a number. They only have limits. It's always lighter than this, lighter than this, lighter than this, lighter than this. In the end, we know already that they have to be lighter than 1 electron volt, even less than that, but let's say 1 electron volt for simplicity. And that's something very surprising. Why? Okay, so I made a simple plot here. I put here in logarithmic scale the masses of all the particles in the standard model. So you have leptons, quarks, gauge bosons, and the Higgs. The mass is in electron volts, so neutrino, I said, let's suppose it has 1 electron volt mass, which is already too much, and I put it here. So you see that basically all the standard model particles more or less fall in this region of masses, which is spread but not so much, but neutrinos are here, much below. So for some reason, neutrinos are much, much, much lighter than the rest of particles. And there is no reason for that. If they are all coming from this, if all these masses are coming from the same mechanism, the Higgs mechanism, we don't have a simple understanding why this big difference. If everything is coming from the same place, they should be more or less the same. Of course, you can say, okay, it's just like this, but we would like to have a better understanding. And this makes neutrino a little bit special and leads to many questions. So nowadays, when people propose extensions of the standard model that have neutrino masses, the main question is why neutrinos are lighter than the rest of particles. If you can't explain that, then you are not doing anything better than the standard model. So let me conclude this big introduction about the lepton sector with some open questions. I don't have the time to go through them, but okay. This was just a sketch of the lepton sector, but there are many questions you could ask, and we don't have answers for them. So we don't know whether I already discussed about the origin of neutrino masses. We don't know whether there is something special. But there are also open questions about whether they are Dirac or Majorana, because there are two types of fermions you could have, Dirac and Majorana. And neutrinos could be Majorana, that we don't know yet. We don't know the absolute scale of neutrino masses. We haven't measured neutrino mass. We know it's not 0, but we don't know how much it is. We don't know the mass ordering. This has to do with the fact that since you have 3, and we have measured already, or people have measured, 2 different mass difference among them, you could order them in different ways, and we don't know yet which one is the right one. Also, maybe there are more than 3 neutrinos, and there are some experiments with some anomalies that may be pointing to the existence of some additional sterile neutrinos. We don't know whether there is CP violation in the lepton sector. We know there is in the quark sector, maybe also in the lepton sector, but we don't know yet. So as you see, this is a very active field of research. There are many open questions, and I mean, people have been proposing models, proposing ideas, making experiments to solve these questions. I mean, it's a very active field. So with this, I conclude the introduction. I guess you will be like this. I see some people like this. Okay, let's continue. So now, lepton flavor violation. This is the main topic of the talk, of the seminar. And let's begin with something very simple. As I said, in the standard model, there are 3 copies of the lepton doublet. We have the electron copy, the muon, and the tau. They come in 3 flavors. And in the standard model, there is nothing connecting guys which are in different copies. So there is no interactions between these guys and these guys, or these guys and these guys and these guys and these guys. This allows us to define something like flavor, which is belonging to this, or to that. This is the flavor. You call these guys electron flavor, muon flavor, and tau flavor. And the question is lepton flavor a conserved quantity? Is there any process in nature that changes from one to the other? And we already know the answer, of course. There are processes that violate flavor. We have already mentioned them. Neutrino oscillations are by themselves a proof that lepton flavor is not a conserved quantity, because you produce a neutrino with a given flavor, and in the propagation it changes. So you violate lepton flavor. However, we have never observed any process with lepton flavor violation involving charged leptons. We have only observed processes with neutrinos, never with charged leptons. And in principle, this could be observed as well. I mean, for example, there is nothing preventing a muon from decaying to an electron and a photon. There is no symmetry besides lepton flavor, which we already know is broken, that prevents this from happening. The same here, the Higgs could decay to a couple of fermions with different flavors, like a muon and a tau, or a tau could decay to 3 muons, or 2 muons and anti-muon. There is nothing preventing this from happening, but this has never been observed. This has never been observed. So why is that? And okay, well, for many years, this was more or less understood using this setup. And this is something a little bit more detailed, but let me explain. So let's suppose we consider the most minimal extension of the standard model you could imagine where neutrinos have masses, the most minimal one. And this is something as simple as having a standard model plus right-handed neutrinos, exactly as in the quark sector. So you have left-handed and right-handed, and you create Dirac pairs. When you do that, your charge current is no longer diagonal, but has some matrix here, which is exactly the analog of the CKM matrix in the quark sector, nothing else. This matrix, in principle, is off-diagonal because neutrinos can mix. You have 3 families, and maybe the matrix could be off-diagonal. So in principle, this U matrix is perfectly general. It's a perfectly general unitary matrix. Now you can compute, for example, the branching ratio. This is the frequency of this process, mu2 e gamma, to happen. And your computation is as simple as this. You obtain a result that depends on this matrix here. You have to take the sum over all the 3 elements here, K1, 2, and 3, because you may have 3 different guys propagating in the loop. And the problem is that in this model, the only source of lepton flavor violation is neutrino masses. So you already know that any process that violates lepton flavor has to depend on neutrino masses, because this is the only seed you have, the only source. So because of that, your final result is suppressed by this ratio. Neutrino mass squared divided by W mass squared, and then square. Because of that, since neutrinos are very light, the branching ratio for this is 10 to minus 54, which is basically unobservable. There is nothing in the universe that could be searched for with such a small fraction of events. So if you are living in a universe with a standard model plus Dirac neutrino masses, you would expect that only neutrinos feel lepton flavor violation. And this is very sad because this is the truth. Then we are done. We cannot observe anything. However, we have good reasons to believe that this is not the case, because if you do that, you cannot explain why neutrinos are so much lighter than the rest of fermions. And it turns out that as soon as you create a little bit more complicated extension of the standard model, this expectation that I just mentioned doesn't hold, and you get much larger branching ratios. Much larger meaning observable branching ratios. So in general, the majority of beyond the standard model models predict very large lepton flavor violating branching ratios. And it's something very simple to estimate. For example, if you consider that you have an operator like this, a 4 fermion operator with a mu-e flavor violation, you can easily check that using current bounds on these processes, on mu to 3 electrons, for example, you get a constraint like this. So you are probing energy scales which are much higher than the one in the standard, than the electron scale. So in general, in most models, these quantities will be much, these coefficients will be order 1, and this will be 100 GeV, and then you will be excluded already. So this is a typical problem in many extensions of the standard model. And let me show you some examples. For example, let's consider supersymmetric models. In supersymmetry, you have many particles. We don't need to explain this here, but let's just mention that there are some particles called leptons, which are just scalar particles, just like the leptons, but scalar, so spin 0. And they can mix. So there is a lepton called muon, and there is a lepton called selectron, and they come with the same flavor as the muon and the electron, and they can mix. They can have a term in the Lagrangian that mixes them. If this term is not 0, you can draw these Feynman diagrams, and then you generate mu 2 gamma. So people have computed this in much detail, and they have found that these quantities, which in principle could be whatever, have to be tiny in order to be consistent with the current bounds on lepton flavor violation. Another example, there is a model called the Babu-C model, and this is a popular model where neutrinos get masses at 2 loop. Not important here. And in this model, there is a guy, usually called K, which has a charge -2, and this guy can couple to 2 leptons. And there is no reason for this coupling to be diagonal. It can couple to electron and muon, or muon and tau. It could be whatever. And then you can calculate, and you see that there are processes like this. So you have a lepton with a given flavor that can decay to 3 leptons of a different flavor thanks to these couplings. You calculate, and your branching ratio will be dependent on something like this. So either your couplings, your off-diagonal couplings are tiny, or this guy here is very heavy, and then you get a suppression. So in general, in many beyond the standard models, you expect large lepton flavor violation. That's why this is important. Another reason why this is important is because there are experiments. When there are experiments, you feel more motivated to study this because you know that there will be an answer, whether this is true or not. And in particular, here in this table, I show you the most popular lepton flavor violating processes. So you have processes like this, where a lepton decays to another lepton and a photon, or a lepton decays to 3 leptons, or this is a bit more complicated. This is a lepton that converts to another lepton interacting with a nucleus. This is a little bit different, but this is interesting for other reasons, experimental reason. And here you have the current bounds. So the rates for these processes have to be below these numbers. We know this already. And if you compare these numbers with the ones on the right, which are future plans for improving these numbers, you see that in some cases there are minor changes, like this one, for example. Okay, this is 1 order of magnitude, not so important. But in some other cases, for example, here we know already that this rate has to be below 10 to the 12, but there is a plan for an experiment called mu3e that promises, we have to believe them, to be able to measure rates which are higher than 10 to minus 16. So if they don't see anything, there will be a huge improvement in the bound. Maybe they see something, they see an event. also here you see fantastic improvements. Currently, the best bound is here, 7 × 10⁻13, and there are plans in COMET and in Me2E for limits which are about 10⁻18, 10⁻17, and there is another project, this is in Japan as well, at the level of 10⁻18. So it's really an amazing number.
Avelino,
Yeah.
all these experiments are planning, you said one is in Japan, but the rest is...
I have a slide with a map. Okay, it's the next one, so you don't have to wait. Okay, well, this is just to show the evolution of these experiments. So in the 40s and 50s, we know that the limits were at the level of 10⁻3. Now we know that they have to be below 10⁻12, 10⁻13, and in the next few years, bloop, we will go here. So it's really amazing how these things have been improving continuously. Every time a project was finished, they said, okay, we cannot do better, but then somebody came out with a new idea for a better technology, and then they found a way to improve the limit even more. And now, answering your question, these are the locations for the experiments. Me2E, which is Me2E conversion in nuclei, is in Fermilab in Chicago. And in Europe, we have 3 experiments, and the 3 of them are in Switzerland. They have a lot of money. And one of them is, of course, the LHC. You can also look for lepton flow violation at the LHC. And the other 2 are Mu23E and MEC. And these are in PSI, which is a lab in Zurich. So this is also, they have actually the most powerful, the most intense cyclotron in the world. So they need a lot of muons to make these experiments, and that's why they can make this experiment in this place. And then the best in this are the Japanese. They have many experiments. So they have these 3 experiments looking for Me2E conversion in nuclei, DIM, COMET, and PRISM. And then BEL2, this is still under construction. This is a big factory, which could be helpful as well in processes involving taus. So you see. And now regarding years, so MEG is already old experiment. They have already limits. But they are planning to make an improvement for a second phase. And this is supposed to begin in 2016, 2017. This always takes a little bit more than expected. Then Mu23 has not started. They are still constructing, but in principle it should begin in 2016, so next year. LHC, you know, and DIM is already about to begin. I don't remember the dates, but I think it should be 2015, so this year. And COMET is for 2018, I think. And then PRIME is in the longest period. I mean, this is for the future. This could be 2020 something. And Mu2E is basically like COMET, 2018, 2020. Now, I said that there are plans for improvements for limits of the level of 10⁻18. And this is a very impressive number, but you don't realize how impressive this is until you make some estimate. So to touch this number a little bit. So since I'm in Valencia, I thought that there was a very simple way to understand this number, and I make some computation. So I found on the net that there are about 5,000 rice grains in one portion of paella. So every time you eat paella, you eat about 5,000, okay? So I did an extrapolation, and I calculate that a paella with 10⁻18 rice grains has basically the size of the Earth, basically. So imagine finding one rice grain in a paella of the size of the Earth. So this is what these people with these experiments are trying to do. So it's really, really, really very complicated. They have very powerful muon beams because they need to study 10⁻18 muon decays to see one event basically happening in the channel they want to measure. So this is something really, really, really impressive. So, okay, imagine this paella, really impressive. The background is basically 0. It's basically, well, I mean, it's not 0. The physical background is 0, but there are other backgrounds. So they may misidentify an event, they have accidental backgrounds, but in the standard model, this is 0. So if you observe 1, it's already sufficient. Yes, but you need 10⁻18 muons to find 1. So you can imagine. This is something very, very hard. Actually, I found in Wikipedia, I was checking this yesterday, that in these places, they have production of muons at the level of 10⁻10 muons per second. Come on, I mean, this is a huge number. I mean, muons, like hell, no? Amazing. And for a longer period. I mean, they don't do this for a second. They do it continuously because they need to prove this in several years. So it's really amazing. I mean, they are doing a great job, I think. So let me continue. So as I said, there are many processes that you can look for in lepton flavor violation. So the question is, what should I look for? Should I put all my money in one of them, or should I diversify? And the answer is, of course, you should diversify. And the reason is that if you discover lepton flavor violation, you just get one number. You measure the branching ratio for, let's say, tau to E gamma. And then what? You don't learn much. You know one number, that's it. But if you measure lepton flavor violation in different processes, you can extract some information. And in order to show that, I took this table from this nice paper. From this nice paper. And basically what they do is they consider several models, they compute some observables, and they take ratios of observables. So, for example, here, they consider the branching ratio of mu to 3 electrons divided by the branching ratio of mu to E gamma. And they do it for 4 models. These 4 models are a little Higgs model. You don't need to know what it is. This is not important at this point. This is the MSSM, which is a supersymmetric model in a particular region of parameter space, which is called dipole. There is another region which is called Higgs. And then this is the standard model with 4 generations. We have 3. This is the standard model with 4. And they find that these numbers are very different in different models. So this is the game. If you ever measure these numbers, you can identify, or to be more precise, you can exclude some scenarios. For example, imagine you measure this ratio here. I think this is the very representative. And you find something at the level of 10. Then, by looking at this table, you see that the only one that can have 10 is this one. So you basically exclude these 3 options. And you can do the same with other quantities. So the lesson we learn from this table is that one number doesn't tell you anything. But if you have 2 numbers, you can start looking for correlations, patterns, relations among observables. And by doing that, you can learn about the physics that is behind. And this is what we want. We don't want to get a number. We want to learn about nature. Let me show you an example. So for many years, people have discussed supersymmetric models. And one of the things they have done is, let's consider models where lepton flavor violation takes place. And let's see what is the dominant contribution. Because in general, there are many contributions. But let's see what is the dominant one to processes like lepton to 3 leptons. For example, a muon that decays to 3 electrons or something like that. And then, as I said, you have something like this. You have a muon, for example, that decays to 3 electrons. And in general, you can have many things taking place here. At the 1 loop level, you have many diagrams. At the 2 loop level, you have many more, and so on. But people have found, by doing very complicated analytical calculations, that in most cases, in many parameter points, the dominant diagram is something like this. So you have something like a lepton that decays to another one and a photon, and then this photon is attached to 2 leptons. And this is called the dipole contribution, and since this one dominates, people have called this situation dipole dominance. Now, suppose you are in this dipole dominance, which is basically what I showed here, this dipole. Then you can see already that this diagram is basically the one that leads to lepton gamma times the coupling of the photon. It's basically the same diagram with some additional particles, nothing else. Then if you do that, you can see that there must be a relation, a very simple relation between these 2 different branching ratios. If you know one of them, you can compute the other. And actually, it turns out that if you do this calculation, you get a result like this. It depends on alpha, which is basically this coupling, times a function of these 2 masses, the mass of this guy and the mass of this guy. Now, you can easily check that this number here is small. It's something like 1/100 or something like that, like 10 to minus 2. And then you conclude immediately by doing this calculation that if you are in this model, you expect the branching ratio for lepton to lepton gamma to be much larger than the one for lepton to 3 leptons. That's one of the reasons why people have put so much money into this process, because they were expecting this to be easier to discover than the other one, because it has a larger ratio. But of course, this is something very particular of this model. So if you, for example, measure these two guys, these two branching ratios, and it turns out to be the ratio, let's say order 1, you exclude this model, but there are other models where this ratio could be different. So this is the way we have to play this game. We have to measure different quantities, understand the relation among them, and then extract information about the basic physics. And this is what I basically synthesize in these points. So this is what I call the lepton field violating program. We have to measure lepton field violation in as many observables as possible. Only one doesn't help. And then if we understand what is the relation between the different observables, what is the possible pattern among the different contributions, then we will be able to understand the underlying physics in case an observation takes place. And given that in the next few years there will be many experiments looking for these processes, I think it's the right time to do it. We have to do it right now, because otherwise this experiment will come up and we will be late. So this is basically the main lesson that I want you to get home about lepton field violation. Now I think I'm doing fine with time, so let me move to more, let's say, detailed parts of the talk. So first I want to discuss something that has been in the literature recently, and there have been many papers on this, which is lepton field violation in low-scale seesaw models. And first of all, let me define what is a low-scale seesaw model. So as I said, there are many extensions of the standard model where neutrinos get masses. The most popular one is the so-called seesaw model. And in this seesaw model, there are some right-handed neutrinos which are super heavy. And because of these guys being super heavy, you can explain why the normal neutrinos are light. This is a kind of, this is a mechanism that explains why these guys are light by putting the other guys too heavy. However, if you do that, these guys which are so heavy don't contribute to physical processes because their contribution is suppressed by their mass. So people came up with some ideas for models which share some of the ideas with these seesaw models, but have a totally different perspective regarding the mass of these guys. And this is what people call low-scale seesaw models. And the most common one, the most popular one, is the inverse seesaw. Here you have the normal right-handed neutrinos, which are here, and they have the typical Yukawa coupling with the normal leptons and the Higgs. But instead of a Majorana mass for the right-handed neutrinos, in this model, they have a Dirac mass with another guy, which is called S, and this guy has a Majorana mass itself. Then you can compute the mass matrix in this model, and you get something like this. It's a little bit different from the usual seesaw. And if you go to the limit in which this quantity here, which is nothing but this one, is much smaller than this quantity, and this quantity is much smaller than this one, you can obtain analytically that the mass for the neutrinos in this model would be something like this. So you see that the mass of the neutrinos in this model is proportional to this mu s, which by assumption is a small number. Now, if this is a small number, you can make it really small. You can make this number as small as, for example, 100 kb or a kb or something like that. Then, if these guys are at the TB scale, everything is fine with Yukawas which are order 1. So the nice thing about this model is that you can have right-handed neutrinos and they don't have to be that heavy. They can be lighter. And if they are lighter, they can participate in processes. And this is what you want, because then you have new effects. You have new physical effects that you can look for in experiments. So basically the idea is that if the standard seesaw is something like this, the inverse seesaw would be something like that. So it's the other way around. Instead of having a very large scale, you need to have a very small scale to suppress neutrino masses. So you play the other game. Now, people have known that these type of models have very nice perspective for lepton field violation for very simple reasons. And there is a simple way to understand it. Since you have new right-handed neutrinos living at the electroweak scale, so they are light, they can participate in loops like this. So now the neutrinos that propagate here are not the normal neutrinos, but are the mixture of these neutrinos with the right-handed neutrinos. And then the suppression that we obtained and we discussed before in the introduction doesn't take place, because these guys can be heavy, as heavy as the W. So we can go back to that formula. You remember there was a formula with m neutrino divided mW. This doesn't have to be a small number. In this case, it could be large. Because of that, you break this suppression, and in principle, you can have large rates for processes like mu3 gamma. And this was known already for many years. More recently, people have realized that something similar happens in processes like this. So you have these types of box diagrams. They are called box for obvious reasons. And again, you have neutrinos propagating here. And again, these neutrinos are a mixture of the normal neutrinos with the right-handed ones. And because of this mixture, there is no suppression, and this could be really large. And this could lead to processes like mu2e conversion in nuclei. Here you have the nuclei, these are the quarks in the nuclei. And this has been discussed by many authors. This is something that has been discussed in much detail recently. However, to make a long story short, let's say that there were different papers claiming different things, slightly different, and there were some confusions. So we decided to solve the problem for once and forever, and we did a very complete study of this type of models. So we computed in supersymmetry and without supersymmetry all these processes. So lepton to lepton gamma, lepton to 3 leptons, and mu2e conversion in nuclei, including all contributions, meaning this, and all contributions that you could have. So we got like a few hundred Feynman diagrams. It was really lengthy to compute, but we had some tools. I will explain later how we did it. And we came out with some results. So since I don't want this to be too technical, let's just say that we studied for different observables, which are the dominant contributions, to understand what are the ratios one expects between different observables. As we said before, this is the important number you want to study. For example, here we studied mu2 as a function of, in this case, the supersymmetric mass, and in this case, the mass of the right-handed neutrinos. And we found that depending on these masses, the different contributions which are drawn here in different colors may be more relevant or less relevant. For example, let's go to the diagram on the left, the plot on the left. Here we have, in black, the total contribution, so the total branching ratio. And in the different colors, we have the different individual contributions. For example, we see, here, you cannot see it very well, but you can believe me, these are the non-SUSY boxes, the non-supersymmetric boxes, this dot line in blue. And we see, for example, that when MR is small, they are totally dominant. So basically, you cannot distinguish between the total rate and the individual contribution. They are basically the same. But when MR is large, so when you are here, this one goes down, and this purple line, which are the SUSY, the supersymmetric photon penguins, start being more important, and then eventually they dominate. So you expect totally different results depending on whether you are here or you are here. In fact, if you are here, since the photon penguins dominate, you would expect the branching ratio for this guy to be, as I said before, let me go back. You expect this, exactly this, because this is the photon penguin, there's nothing else. So by doing this type of studies, you can see how the result will look like in different regions of parameter space, and you are able to see whether you can depart from the usual expectations in some cases. We did the same here for the supersymmetric mass, and you can see that again, there are contributions, like for example these supersymmetric penguins, which are very relevant for one scale, but not so relevant for a different scale. So this basically is the idea. Now I said that we computed several hundred diagrams, and this was possible. This is kind of a propaganda slide. We did it because we developed a code to make that computation, because otherwise you have too many diagrams to compute, and by hand this takes a long time. We were several people, but not enough to do this. So, okay, this is just to mention that if you're interested, we developed a code called Flavor Kit that does this calculation for you automatically, so you don't need to do anything by hand. So this is nice. This is for lazy people, like me. Now, let me move to another topic. This is something also hot. This has been discussed recently, which is Higgs lepton flavor violating decays. So you know we have discovered the Higgs. So one question is it possible that the Higgs decays to leptons with different flavors? And the answer is, of course, it is possible. Let's see. So people have considered this, and after many years, these papers were kind of forgotten, but now with the Higgs being discovered, people have again discussed this, And for example, these people found that if you take the current limits, the branching ratio for processes of this type are at the level of 0.1, which is not very impressive. But some other people said, okay, if you take the LHC at this energy and you work hard, you may get at the level of 10 to minus 3. So this is something that in principle could be looked for. And in fact, recently, CMS, which is one of the major collaborations at the LHC, announced that they found a little excess in the Higgs decaying to tau mu. This is, of course, nothing to take too seriously because the statistical significance is not very large. It's 2.5 sigma. But, okay, well, it leads to speculation if you want. You see the excess here. So at a mass which is the Higgs mass, the bump is a little bit too much. And in fact, the thing is that they have looked for this in several channels, including jets, without including jets, and they found a significant excess in more than one. So it's something consistent in more than one channel. So you may take this seriously or not. I will take it seriously because otherwise the game is over. I want to play with this. And if you take it seriously, their measurement would be of a branching ratio of this level. So at the level of 1%, basically. So every 100 Higgs, one of them decays to tau and muon, according to this result. This is a very large number. I mean, 1% is a lot. For example, the decay in the standard model of a Higgs to 2 tau is at the level of 6%. So tau mu would be only 1/6 times the 1 for tau tau, which is flavor conserving, and you would expect much more important. Of course, this needs more statistics. You need to accumulate more data to see whether this was just a fluctuation or this is something relevant. And of course, you need the other collaboration, Atlas, to check it. Maybe this is wrong and only CMS sees because they have some error in the calibration of their detectors. But let's take it seriously at the moment and let's ask the question, is there any model that can reproduce this? And this is not so simple. In fact, people started to work on this, as you see, in the last 2 years. And many people tried to find a model in which everything is consistent and you can have Higgs to tau mu at the level of 1%. And they failed, basically. So, for example, these people working in the MSSM, they found that the best you can do is 10 to minus 4. And we're talking about 1%, which is 10 to minus 2. So it's 100 times smaller than that. This was the same in R-parity, supersymmetry, R-parity violating supersymmetry. This is with vector like leptons in the inverse seesaw. So people really got crazy trying to find models where this was possible. But always it was the same problem. Every time you wanted to increase the branching ratio for Higgs into tau mu, you found that you were exceeding some limits. So you were forbidden to do that. You cannot exceed the other limits. So there was some tension. And so the conclusion was, is there no hope? However, well, some people pointed out that in fact there might be a model where this is possible. And this was the type 3 2 Higgs doublet model. So 2 Higgs doublet model is just the standard model where you have 2 Higgs doublets instead of 1, nothing else. And type 3 means that you allow the 2 Higgses to couple to everything. There are versions of the 2 Higgs doublet model where you allow 1 Higgs to couple to quarks, the other to leptons, and you can make different combinations. The type 3 is everything couples to everything, so total freedom. And in general, in this model, you have a coupling of the Higgs to 2 different fermions, and this coupling could be of diagonal. It's a general coupling. So people discussed this and made some estimates and concluded that in principle it is possible to have a branching ratio at the level of 10 to minus 2. So since I wasn't sure, I wanted to see it by myself. So together with a nice collaborator, we basically worked it out, and we included direct searches, constraints coming from flavor, tau to mu gamma, the measurements of the Higgs couplings, because today there are so many constraints that it's really hard to find a new signal. There are always constraints killing you. And we found that in principle it is possible. So yes, we conclude that yes, it is possible. So here I show you a plot where I have the branching ratio of Higgs to tau mu as a function of the branching ratio for tau to mu gamma. And you see that there is some kind of correlation, although it's not perfect. There are many points which are outside the correlation. But given that the current limit for tau to mu gamma is this line, so everything which is on the right of this line is forbidden, is already excluded. In principle, you can be in this band, which is the band observed by CMS. So there are points which fulfill the measurement by CMS and are still fine. Questions? No? Okay. So unfortunately, there is no prediction. If the correlation was perfect, you could predict. You could say, okay, I expect this. But as you see, there are many points which are outside the correlation. And this is a bit unfortunate. But this is how it is. Now let me make a few comments about this result. Well, one of the things that is really curious about this is that, as I said, this coupling here, which is the diagonal coupling of the Higgs, is totally general. Could be whatever. It's a matrix with entries, which are numbers, and that's it. However, the number you need to reproduce the CMS result is basically this number here. So the number you need is very close to the ratio between this product of masses divided by the Higgs wave. There's no reason for that. It could be totally different. It could be 10 times that or 10 times below that. There's no reason. The fact that there is a very close number coincidence between these two quantities is something very intriguing. And it may be that there is some flavor symmetry at work, because these type of relationships are typically found when you have flavor symmetries in your model. So this may be something interesting to look for. Another comment that I wanted to make is that in this model, you expect the decay of tau to 3 muons to be much smaller than the one for tau to mu gamma. If this is the case, since here you see that tau to mu gamma cannot be larger than 10 to minus 8, and given that the experiments looking for this are not so sensitive, if they ever found this process at the level of, let's say, 10 to minus 9, this model would be excluded. So there is a way to see whether this explanation is true or not. Or it's not true. Of course, to make it true, you cannot know. And with this, I basically conclude. So let me make some final comments to motivate you. So I really think that lepton feather violation is going to be very important in the next few years as an alternative to LHC physics. Experiments are going to take place very soon, and in a few years there will be results. When this happens, maybe we have discoveries of new processes, maybe not. But in any case, I think we have to be ready for that, to understand what you would expect in different models, the different correlations, patterns, and I hope you like the talk. Thank you.
Questions, comments? Any doubt about the lepton flavor? In fact, I want to have a question. In this, when you were analyzing this, the contribution of different SUSY processes to the lepton flavor violation.
You mean this?
Yes, exactly. These SUSY processes are SUSY processes in which the mass spectrum, and everything could be observable in the AC, or is a SUSY that is unobservable?
Well, for these plots, we took everything to be at the level of 1 TeV, so in principle observable.
Okay.
But of course, it depends. Actually, to be more precise, you cannot see it here, but in this plot there is here a gray band. Maybe you can, the ones which are in front of it can see it. Everything which is on the left of the gray band is excluded already, because it would imply very light supersymmetric particles, and they have it looked for, and we didn't find them. So in principle, if you are here, yes, you are at the edge. You can see it, maybe.
Yeah, I guess I got it in the camera. Other questions? No, I guess everything clear, but I had another question, but I forgot. Because you passed it too fast, but anyway. No. Okay, so we thank Avelino for the... Next seminar is going to be at the first week of March, but I don't remember who is going to give it. Okay, but anyway.